All right, here we go with podcast 2.4 for AP Chemistry, and we're going to talk all about redox reactions. So a redox reaction, or an oxidation-reduction reaction, we call them redox for short, is just a reaction in which one or more electrons are transferred. That is most of the reactions that we talk about in chemistry. So if you remember, single replacement reactions, those are all redox reactions. Combustion reactions are all redox reactions. This is that third type of chemical reaction that we haven't talked about yet. They're important to us because many of the reactions that produce energy are redox reactions. So the examples they give here are photosynthesis and combustion reactions. Both of those produce a lot of energy that we use, both in our body and then in the world around us, and both of them are redox reactions. So here's an example of another redox reaction. This is when we take sodium metal and we join it with chlorine gas. We get a lot of heat produced, a lot of energy, and you get sodium chloride, table salt that you can eat. So electrons are transferred between the sodium and the chlorine gas, and you end up with NaCl. We are going to have to keep track of those electrons. So to do that, we use what are called oxidation states. And oxidation states are the same as oxidation numbers. You can use them interchangeably. They allow us to keep track of electrons during redox reactions, especially during redox reactions that involve covalent compounds. So there's our covalent compounds. And remember, covalent compounds are when we have shared electrons. So it's a little harder to keep track of electrons because there's not the transfer from one element to another. They're sharing them. If we have covalent compounds, we need to remember that electrons are split evenly between two identical atoms. So if I have O2, the oxygens are going to split the electrons evenly, and then electrons are going to be assigned completely to the atom with the higher electronegativity. If we're dealing with ionic compounds, then we're just going to use the charges that are associated with those ions. So here's some rules. This is already written in your packet. Rules for assigning oxidation states. An oxidation state of an atom in an element is 0. So if I see O2, because that's elemental oxygen, each of those would have an oxidation state of 0. They wouldn't have one. If I see sodium and it's solid sodium, that would have an oxidation state of 0. If I see fluorine gas, each of those are going to have an oxidation state of 0. Oxidation state of monatomic element is the charge. So if you go like sodium with a plus charge, that has a +1 oxidation state. Oxygen has always a -2, except if it's peroxide, like hydrogen peroxide. Each of those oxygens would be a -1. Hydrogen's always a +1 in covalent compounds. Fluorine is a -1. The sum of all your oxidation states have to equal 0. So if I have NaCl, the Na would be a +1, the chlorine would be a -1, and I add those up, and they equal 0. That's what they're talking about here. And the sum of your oxidation states need to also equal the charge of an ion if you have one. So for example, if I have the nitrate anion, when I add up all my oxidation states, they need to add up to a -1. And we're going to do some practice problems with these. So here we go. You have this list in your packet, but we're going to do them in a different order. We're going to leave this top one for last. So we'll get to that one in a second. We're going to start from down here. The rules said that fluorine is always a -1. So fluorine is a -1. Well, I have 4 of them. So 4 times a -1 is a -4. And since I only have 1 of these, this must be a +4. Chlorines are a -1, and I have 5 of them. So 5 times -1 is -5. And I only have 1 phosphorus, so this must be a +5. Oxygens are always -2, and I have 2 of them, so that's a -4. So this manganese must be a +4 to balance it out. And here's our ions, so we need to watch out for this. My oxidation numbers need to add up to a -2. We know that oxygen is going to be -2, and -2 times 3 is -6. So if down here all my oxygens give me a -6, this carbon can only be a +4 because a +4 plus a -6 is going to give me the 2 negative charge that I need for this carbonate ion. And last one here, I'm going to do these individually. This has a charge of -2. So each of these potassiums must be a +1 to balance out that -2 charge. But then if we look in here, we know an oxygen is a -2, and -2 times 7 is -14. So I need my chromates to add up to -12 because a -12 plus a -14 is a -2. And we know that -12, if we had that, or they would have to be a +12, I'm sorry. If this is -14, this has to be a +12 to balance out to a -2. So each of these must be a +6. So potassium is a +1, chromate is a +6, and oxygens are a -2. Carbons are the +4, oxygens are the -2. Be careful when you're labeling what the oxidation numbers are that you don't, instead of saying that this oxygen is a -2, don't say that it's a -4 because you went and multiplied. You need to make sure you give just the oxidation number for one of those atoms. And we'll do a lot more practice with this in class. All right. These are characteristics of redox reactions. So we're going to see a transfer of electrons, and the transfer may occur to form ions. So we may go from having sodium, the solid, to having the sodium ion. All it takes is electrons being transferred. Oxidation is an increase in oxidation state, so that means that your oxidation number goes up. Reduction is a decrease in oxidation state. That means that your oxidation number goes down. And if you're having your oxidation number go up, it means you must be losing those negative electrons. And if you're getting your oxidation state to go more negative, if it's going down, you must be gaining those negative electrons. Here's a visual to kind of help you with this. I have my metal and I have my non-metal, or my X. The metals we know tend to lose their electrons, so the electron is transferred from the metal to the non-metal. This is the oxidation-reduction process. And then our non-metal likes to pick up those electrons. So that is being reduced because it's gaining more electrons than it had. If it gains electrons, its oxidation state is going to go down, and it's going to be the oxidizing agent. But that's confusing. We'll get to that in just a second. So if it's being reduced, it's going to gain electrons and its oxidation state is going to decrease. Your metal, which is losing electrons, is going to become more positive in terms of its oxidation state. And then this agent thing down here, the agent means it's causing the other process. So if it is being reduced, it's going to cause the oxidation. If this is being oxidized because it's losing electrons, that means it's the reducing agent because it's causing the reduction in the other element or ion. There are two little sayings down here that you need to remember. Oil rig, that is oxidation. I don't think I need to write all these out. Oxidation involves loss. Reduction involves gain, and that's in reference to the electrons. So oxidation involves loss of electrons, reduction involves gain of electrons. And then the other one is lose electrons oxidized, gain electrons reduced. And either of those you can use as a little mnemonic device to help you remember what's being oxidized and what's being reduced. So we're going to do some more practice here. We're going to identify what's being oxidized, what's being reduced in these redox reactions. So we said that anything in its elemental form, like solid zinc, would have an oxidation number of 0. And I'm going to look for anything else that I can quickly label, and that would be hydrogen gas would also be 0. So chlorine, -1, hydrogen +1, chlorine, -1. There are, we'll just make that a big negative, -1. There are 2 of them, so 2 times -1 is -2. That means the zinc is a +2. All right, so I need to look. The zinc is going from a 0 to a +2 charge. It's becoming more positive, so it must be losing electrons. And if you lose electrons, you're oxidized. So I'm going to write that the zinc is oxidized. And then if we look at the chlorine's going from a -1 to a -1. Nothing is happening. The hydrogen's going from a +1 to a 0. It's becoming more negative. So the hydrogen is being reduced. It's gaining electrons. Next one, we have copper 1 chloride giving us copper 2 chloride and copper solid. This one's a little tricky. Chlorine we know is -1, so this copper must be a +1. Chlorine again here, -1. This copper then, since there's 2, must be a +2. And we have another copper solid over here by itself, and that's its standard state, so it's 0. Nothing is happening to the chlorine. It's staying at a -1. That means that both the copper is being oxidized and it's being reduced. That may seem weird, but we're dealing with 2 formula units or 2 compounds or 2 ions of copper because this is 2 of these things. So one of those coppers is being oxidized and one of those coppers is being reduced. So we would just say down here that copper is being both oxidized and reduced. It's a little different, but it's okay if you have the same thing being oxidized and reduced. Okay, not only do we need to know about redox reactions, we need to be able to balance them. And because it involves electrons being transferred, it is not as simple to balance these as it is your normal everyday equations that you've been doing. Here are the rules. They're written down. The big one you need to watch out for is right here. These are the really important steps, these 4 steps right here. You want to balance all the elements except hydrogen and oxygen. So you would balance your bariums, your coppers, your chlorines, your whatever you have that's not hydrogen or oxygen. You balance it first. Then you balance your waters. You use waters to balance your oxygen, and then you use hydrogen ions to balance the hydrogens. And then after that, we add in electrons to balance the charge on both sides. This is called the half reaction method because we separate the equation just like the ones we were looking at. You're going to get 2 reactions. You're going to write the oxidation reaction and you're going to write the reduction reaction. You're going to have to balance both. And then you're going to multiply to make your electrons the same, and then you'll add them back together at the end. So we separate them to balance both parts, and then we add them back together at the end. So here we go. We're going to try 2 of these. And you need to pay attention to whether it says acidic or basic because that does affect how you kind of end your problem. The 2 that we're going to do right now are both acidic. So it says balance the following redox reaction that occurs in acidic solution. We have the dichromate and the sulfite giving us the chromium ion and the sulfate anion. So what we're going to do, I don't really need to know which one is the reduction reaction and which one is the oxidation reaction. I just need to write the half reactions that go with them. So here we go. I'm going to put the dichromate. We're just going to start over there. All right, we're going to do the dichromate, and that goes to the chromium. And then my other one is going to be the sulfite going to the sulfate. You kind of match up. The chromium is in both of those, and then the sulfur is in both of those. So those are my 2 half reactions. I'm going to focus on one at a time. I want to balance everything that's not an oxygen or a hydrogen first. So my chromiums, I have 2 on this side and only 1 here. I'm going to put a 2 out in front. Then I'm going to use waters to balance my O's because I have O's on this side but none on this side. So I have 7 oxygens. That means I need to add 7 waters to this side so that I have the 7 O's over here to balance the 7 O's on this side. Then the third step is to balance your hydrogens using the hydrogen ion. So I have 7 times 2 is 14 hydrogens on this side. So I've got to add my 14 hydrogens over here. And then lastly, we have to use electrons to balance the charge. So 2 times a positive 3 is a positive 6. This is neutral, it has no charge. On this side, I have a positive 14 and a negative 2. So this side is a positive 12. That means that I need to, because I'm using electrons, I can only make things more negative. I can make this more negative to make it equal to a positive 6 by adding 6 electrons. If I add 6 electrons, the 6 negatives are going to balance out there and make it be a positive 6 to balance this side. So this half reaction is done. Then I come down to this one. I have 1 sulfur, 1 sulfur. Then I focus on the O's. I have 3 oxygens on this side and 4 on this side. So I need to add a water. That gives me my 4 O's on this side to match here. Now I have 2 hydrogens over here, so I need to add 2 H pluses to this side. And then I look for charge. So here I have a negative 2 overall on that side, and a negative 2 and a plus 2 is 0. And I can only make things more negative, so I need to make it match up to this negative 2. And I can do that by adding 2 electrons. All right, just like everything else, I'm finished with that one, but I can't add 6 electrons on this side and have only 2 over here. So what you're going to do is you're going to multiply that whole second reaction by 3. That way your electrons will be 6 and they will cancel each other out. So I like to draw a line because it's like I'm going to do a big addition now. And I'm going to take all my reactants and put them together, all my products and put them together into one huge reaction right here. Since I know the electrons are balanced and will cancel each other out, I'm not going to include them. So I'm going to start with the 14 hydrogen ions and the dichromate ion. That's my 2 reactants there. Here I'll have 3 waters and the 3 sulfite ions. Give you 2 of the chromiums and 7 waters. And then down here we have 3 of the sulfates and 6 hydrogens. So take a second, make sure you can track all those came down here, all these drop down to here. Now what I look for is what can I cancel out? Well, I see that there's hydrogens on both sides. So I have 6 hydrogens and 14 hydrogens. Those 6 are going to go away, and that's going to leave me with 8 over here. And then I also see I have waters on both sides. So these 3 waters are going to go away, and I'm going to be left with 4 right there, and nothing else is going to cancel. So then I just rewrite for my final answer. I have my 8 hydrogen ions, the chromate ion, and the 3 sulfites. That gives me my 2 chromiums and my 4 waters and the 3 sulfates. So I'm pretty sure that's the final answer, but we're going to do our double check. I'm going to box it just to make sure here. All right, so I can check elements on both sides. I should have the same. I have 8 hydrogens, 2 chromiums, 2 chromiums. I have 7 oxygens. Well, let's go 7 and 9 is 16. So I have 12 O's there plus another 4, 16. 3 sulfurs, 3 sulfurs. So my elements are good. Charges, I have 8 of a +1 charge. I have a -2, and I have 3 of a -2. And then I have 2 of a +3, and those are 0. and 3 of a -2. So on this side, I end up with, this is -6, -8, this side ends up as 0, and that should equal this side, which is a +6 and a -6. That also gives me 0. So both my elements and my charges balance. That's the correct final answer for my balancing that half reaction. Okay, next one. We're going to take and make our half reactions. So the bromine there is going to go with that bromine, and the manganese is going to go with that manganese. So I have the bromide ion going to bromine. And you can ignore the aqueous and the liquid. They're not going to affect how you balance your reaction. And then for the second one, we have the permanganate going to the manganese ion. All right, so here I have 2 bromines on this side and only 1 on this side. So I'm going to use the coefficient of 2 to balance those out. There's no oxygens I need to balance, so there's no hydrogens I need to balance. That means I only need to worry about the charge. On this side, there's a -2 overall charge. On this side, there's 0. I can only make the charge more negative, so I'm going to pick this one, and I'm going to add 2 electrons in order to get it to balance out. And I'm finished with that top reaction. This one down here, I have 1 manganese and 1 manganese. Those are good. Then I go to the O's. There's 4 oxygens on this side, so I'm going to balance it with 4 waters. Now I have 8 hydrogens, so I need 8 hydrogens on this side. And for charges, I have 8 plus and a negative. So this is going to be a +7. This side, I have a +2 and a 0, so this side is a +2. +7 and +2, I can only make this more negative, and to do that I need to add 5 electrons to make it match up with that. So now everything is balanced within our half reactions, but now I need to get the electrons the same on both sides. A good way to check yourself before you go much farther is you need to make sure that you have electrons both on the product side and the reactant side. If you end up with electrons on both the reactant side, then you know you did something wrong. You'll always have electrons on opposite sides, so that's a good check at this point to see how you're doing. There's 2 and there's 5. Well, I can only multiply by whole numbers, which means I'm going to have to multiply this one by 5, and I'm going to have to multiply this one by 2. So I do all of that. I'm just going to start up here and work my way down. I have 10 bromides, and I have 16 hydrogen ions, and 2 of the permanganates. That's going to give me 2 of the manganese and 8 waters and 5 bromines, and I don't have to worry about the electrons. So that is what I'm left with. I need to look for things that cancel. I only have hydrogen ions on one side and waters on the other, and those won't cancel, and nothing else is the same. So it looks like that is my final answer. Doing the quick double check, I have 10 bromines over here, 10 bromines on this side. I have 16 hydrogens, and I have 16 hydrogens. 8 O's, there's 8 O's, 2 manganese, 2 manganese, so those balance. This side would be a -10 plus 16 plus a -2, and on this side we have the -4, 0, and 0. So this side is a +4. This side, if I do all the math, I'm going to end up with a -12 and a +16, which is a +4. So my charges balance as well, which means that that is the correct final answer for this reaction. Okay, we said both of those were in an acidic solution. It does change a little bit if you're balancing in a basic solution. So if you think of acids, acids have extra H+, while bases have extra OH-. So what we're going to have to do is we add an extra step. You do everything exactly the same as if it were an acid, all those steps that we were just practicing. Then you need to add hydroxide ions to cancel out all the hydrogen ions, and you add those hydroxides to both sides. So if you have 5 hydrogen ions over here giving us something else, I would have to add 5 hydroxides over here as well as on this side. So what you do to one side, you're going to have to do to the other. This is going to form water, so form water by combining the H plus and the OH minus, and then you'll be able to cancel any waters that show up on both sides, and then we can do the same check to make sure that we did it correctly. Okay, and I picked a little more of a, conceptually harder problem, I guess, because it's set up really weird when you're looking for the half reactions. So if we have this, we have solid silver and the cyanide ion and oxygen gas give us this thing right here, which has a charge. So I go to do this. This silver and the CN2 involves both of these. Those all three go together. So I take my silver and the cyanide to give me this. Don't forget your little negative charge there. Well, what in the world do you do with that? There is nothing on the other side. It's okay, because remember how we said you can balance oxygens using waters? That's what we're going to do here. We're just going to add water to the other side. So this one looks weird, but it's going to end up working out the same way. So I'll start up here. I have silver and silver, carbon, carbon, nitrogen, nitrogen. There's 2 though of those. So I'm going to go ahead and put a 2 out here. That balances everything except oxygens and hydrogens, which I have nothing of. So then I just have to go to my charges. I have a -1 charge on this side, and on this side I have a -2 charge. So I need to make this more negative by adding an electron. Over here we have our oxygens, and I balance oxygens by using waters. So I'm going to add my 2 H2Os to balance out the 2 O's on this side. I have 4 hydrogens. So there's my 4 hydrogens. Now I need to look for charges. This side has an overall charge of 0. This side is an overall charge of +4 because that's 0 and there's 4 positive charges. So I'm going to add 4 electrons to this side in order to make it 0 to balance that side. So I have 4 electrons on this one. I only have 1 there, which means I'm going to have to multiply the top reaction by 4. And then I go ahead and put this whole thing together. So I have my 4 silvers plus 8 of the cyanides plus 4 hydrogen ions and my oxygen. Then I have 4 AgCN2- plus 2 waters. Okay, so I'm to this point, but we said that this one is basic, so I have to keep going. I need to get rid of these 4 hydrogen ions because that tells me it's an acidic solution and I need to make it a basic. So to do that, I'm going to add 4 hydroxide ions, and what I do to one side I have to do to the other. So if I do that, I'm going to draw another line because I'm going to react them together. I still have my 4 silvers and 8 cyanides. But now I have 4 waters, because those come together to give you 4 waters, and oxygen. And then this stays the same, except I'm going to add those 4 hydroxide ions onto the end. Okay, then I look for things I can cancel, which would be my waters. Those go away. That leaves me 2 here. Everything else is fine. So then my final answer is this. And my 4 of these plus my 4 hydroxide ions. So I'm going to trust myself that I did that right because I don't want to waste your time counting charges and elements, even though I think you should do it every time. So there's your final answer for that one. Make sure you pay attention to what they're telling you to balance it in. Oxidation numbers, reduction numbers, or oxidation numbers, not reduction numbers. Make sure you can assign oxidation numbers pretty easily and that you remember the rules and the order for balancing these things. Okay, that is it. So bring questions. If you want to do more practice problems in class, we will definitely do that.